When we think about what makes things break, our minds usually jump to some huge external force, right? A crash, a massive impact, something like that. But what if I told you the most dangerous enemy is often one that's been hiding inside a part from day one, an invisible force just waiting for the right moment to cause a total, catastrophic failure?
I mean, really, let that sink in for a second. It's a pretty wild thought. It suggests that the seeds of destruction could be locked deep inside the very materials we trust to build our entire world.
Well, this hidden enemy actually has a name. It's called internal residual stress. And today, we're going to unmask this invisible threat. We're going to figure out what it is, where it comes from, and maybe most importantly, how engineers are learning to fight an enemy they can't even see.
So what are we actually talking about here? Basically, internal residual stress is a force that's just there. It exists inside a material all by itself. Think about that. With nothing pushing or pulling on it from the outside, there's this constant battle of tension and compression happening deep within its structure. Okay, here's a great way to picture it. Imagine a super powerful, tightly coiled spring, just packed with stored up energy. Now, imagine that spring is trapped, frozen solid, inside a block of steel. To you and me, the block looks perfectly fine, perfectly stable, but secretly, it's holding all this pent-up energy, just waiting to be released. That is residual stress.
All right, so how do these little springs get trapped in the first place? I mean, where does this enemy even come from? Well, they're not there by accident. Kind of ironically, they're often a side effect of the very processes we use to make materials stronger. Take something like a gear. The intense heating and rapid cooling used to harden it can lock in a ton of stress. Or think about welding. As that super hot molten metal cools down and shrinks, it literally pulls on the solid metal around it, creating these huge internal tensions. You'll find it in advanced composites, even in the adhesive used for repairs. Each one of these processes is like a potential crime scene where this hidden stress is born.
So this leads to a massive problem. If this stress is internal, if it's completely invisible, how on earth do you find it before it causes a disaster? Well, engineers have developed a pretty fascinating detective kit to hunt for these hidden forces. Their investigation usually goes down two main paths. On one hand, you've got experimental measurement. This is about physically probing the material to find the stress that is actually there. Boots on the ground detective work. On the other hand, you've got digital simulation, which uses powerful computers to create a virtual model and predict where the stress is most likely hiding. Let's look at a few of these tools. Techniques like deep and blind hole drilling are almost like surgery for metal. Engineers drill a tiny, precise hole and then measure how the material around it relaxes or deforms. That tiny shift reveals exactly how much stress was trapped inside. Then on the digital side, you have something called finite element analysis, which is basically like creating a weather map for stress, showing all the high and low pressure zones inside a virtual part.
Okay, so we found the hidden enemy. Now what? You can't just leave it there, ticking like a time bomb. The next step, of course, is to disarm the threat, to somehow convince those tiny, coiled springs to just relax.
For a long time, the main solution was just heat. You'd bake the part in a furnace and let the stresses kind of even themselves out. But a much more modern and honestly a more elegant solution has come along. And it's not about heat, it's about harmony. It's about vibration.
Yeah, it's a process called vibrational stress relief, or VSR. And trust me, it's as cool as it sounds. Engineers attach a special device that introduces controlled vibrations. They essentially shake the part at just the right frequency. This little jiggle gives the material's internal structure just enough energy to let those trapped stresses redistribute, to find a more stable, low-energy state. The coiled springs, they just peacefully uncoil.
Being able to find and relieve stress is obviously a huge game changer. But the future is about getting even smarter, stronger, and safer. It's about shifting from just reacting to stress to predicting and preventing it with incredible accuracy.
And this is where it gets really exciting. The next big leap is happening where material science meets artificial intelligence. That's right, engineers are now training machine learning models on massive amounts of data to get way better at predicting exactly where these hidden stresses are going to form in the first place.
And the difference is just staggering. As you can see here, traditional computer models, they're pretty good, but the AI-enhanced models, they're on a completely different level. This lets engineers design parts from the very beginning that are just inherently less likely to have residual stress. It's about stopping the enemy before it can even get a foothold.
So why does any of this matter to you and me? Well, because understanding and controlling this hidden enemy leads directly to safer airplanes, more reliable power plants, and stronger bridges. It is the key to making the things we all depend on last longer and work better. And it's what opens the door to creating revolutionary new materials that we've only dreamed of until now.
And that kind of leaves us with one last thought. We've managed to find and start taming this one invisible enemy. But as we keep pushing the boundaries of science, creating materials that are more and more complex, you have to wonder, right? What other hidden forces are just waiting in there for us to discover?